Hello students, welcome back. Let's go back to the type 2 error problem. We talked about this problem. First, straight ahead hypothesis testing. No big deal there. Let me copy and paste this picture. Centered around the null and then looking for the critical value through n-n2 over SE is z-score associated to the level of significance of alpha. 0.01 to the right, alpha to the right, and then 1 minus alpha, 99% to the left. Turned out to be about 2.33. So you can find out the critical value by mu0 plus z value times SE, and it turns out this. And compare that with the observed sample mean. Sample mean is too far away from the null, so okay, let's accept the alternative hypothesis. No problem there. Now let's consider the second case with additional or new hypothesis. Mu is about 31,000 now, not 30,000. Based upon this new hypothesis, let's find out the probability of type 2 error, or the maximum probability of type 2 error. The visualization is this double normal picture. The first is the same as before. Centered around the null, and then critical value, and then null region, which is 99%, and alternative region, 1%, because alpha is 1%. Critical value. We calculated critical value from part A. Let's recycle it. That was 30,870 something, all right? Now, let's consider the second normal graph centered at 31,000. 31,000 normal graph. Therefore, 30,870 something is here. Pretty close to this, but a little bit to the left, all right? And then which is null and which is alternative? Same direction as before here. Blue is null and red is alternative. So this blue part is null, red part is alternative. What about the probability? For probability, I switched the color a little bit so that, blue part here, 99%. And this green part look a little bit different. For this beta value, I want this probability here because I have to follow the new hypothesis. This is based on the old hypothesis, null hypothesis. This one is under the new hypothesis. So, how do you get this area? Well, the picture is there and computation is simple. N minus center over SE. So, critical value 30,700, 3872.4 minus 31,000 over standard deviation over square root of n is equal to, well, nearly 0.34 something. Look up the z table and you're going to get this kind of value there. All right, makes sense? Okay, I hope that made sense. Now let's go to the next problem. Under the new hypothesis, all right, we are staying with the new hypothesis. Find the minimal number of sample size that will limit beta within 0.1. So previously we had 16 tires, n value was there. This time we don't know the n value, but we have to find out. But of course we have additional information. Previously, n was 16. We didn't know beta, we have to calculate. This time it's backward. Beta is there, we have to calculate n value. How does it work? Let me show you the visualization first. It works like this. First picture, the same as before, 99%. 1%. And this time, this mu prime has to be sufficiently far away that this beta, which is aligned here, same critical point, this beta has to be 1%. 10%, excuse me. Previously, previously here, this beta value was 36.7%. Same 31 and 30,000, 31,000. But this probability was much bigger. That means data were more spread out. So bigger standard error, which means smaller sample size, I guess. So the sample size will be bigger than 16. Actually, the answer is already there. We want 30. I don't like giving away the answer that quickly, but anyway, this is the situation. So 99%, 1%, that's the standard. And then we have the second picture of 31,000. And the problem says beta is 10%. So 10%, 90%. So how do you find out X value here from the first picture? You can't. That's a problem. Previously we could because we knew the standard error. Here we don't know the standard error. Sigma over square root of n, we don't know square root of n, so we don't know the standard error. We can find out X value. We cannot find out X value, then how can you get this probability? Do you have a problem? Actually, it's not too much of a problem because we're going to end up with a system of equation. Let's see. From the first picture, this is what we get. X is n. So n minus 10 over SE. Here we don't know the SE, so we use standard deviation of square root of n. And that's equal to the z-score, 2.33. If you look up the table, you're going to get 2.33. But here, I'm using Mathematica, so I'm using a better picture here. Anyway, even if you use 2.33, you're going to get similar number. So solve here, then you're going to get X value like this. You cannot calculate it precisely, but you do have an expression of X in terms of n. Now go to the second picture. All right. Do the same thing, n minus 10 over SE, and do your computation for this area here. And that area is 10%. So by looking up your Z table, getting a Z-score associated with 10%, you're going to get negative 1.28. Really? Where's my Z table? And where's 10%? Yeah, this one. Negative 1.28. Here I'm using a little bit better figure. Negative 1.28155. Anyway. So from here you can solve for X and express X value like this. Now this X value here from the top and this X value from the bottom, they're aligned, they're same critical value. So the first expression and second expression have to be the same. From this equation, I'm going to get an equation of n. Okay, I didn't write the equation of n, so okay, let me write it. There you go. So X is this from the first normal picture, and also it's this from the second normal picture. So setting these two equal, we have an equation of n here. You can solve for square root of n, and then square both sides, and you're going to get 29 point something, but it has to be integers, so 30 or larger. As a matter of fact, here is a little bit more general computation. Instead of all those numbers, I could have used mu0 plus SE, z times mu0 times z times SE, excuse me. So that's how much I go from here to there. And here from mu prime, z times SE, I'm going to the left, so this time it's minus. So mu 0 plus mu prime minus. See, mu 0 plus mu prime minus. All right? So from here, you can solve. So flip this negative to the other side, mu 0 to the other side, like this, all right? And then flip, and then, okay, take reciprocal. Just algebraic manipulation. Solve for square root of n. Got it? And then square both sides, and then you're going to get n value. So you can use this final expression as a formula if you want to. But personally, I prefer to go back to picture and reproduce because I don't want to memorize all those formulas, and also I want to understand what is going on through picture rather than just going through algebraic manipulation and then memorize a formula and just apply it, boom, 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 we have the answer. But after a couple of months, you forget about everything. Now, if you remember visually, then you don't really forget for actually many years. Okay, I don't need this anymore. Okay. And visualization, I talked about it already. Okay, so much for problem C. Now, do we have enough time to do the same thing using the probability value approach? Well, let's do that. After all, our textbook author is using probability value approach. So if you're not really interested in probability value approach, then you can skip this. You can just stick to the visual method like this, aligning critical value. So for probability value approach, it's like this. Under the new hypothesis, mu is about the same as mu prime. So that's a condition now. The probability of accepting H0. We want to find out this conditional probability. That's a conditional probability of type 2 error. And that'll turn out to be a normal CDF value. Why is that? Okay, that's type 2 error. And when do we have H0 accepted? Critical value, X bar, the observed proportion has to be less than the critical value. Let me go back to the visualization here. Look at the first picture. X bar has to fall in the blue region. So the observed sample mean has to be less than the critical value, which is obtained from mu 0 plus z times standard error. So this is critical value. Oh no, excuse me. This is critical value. Mu 0 plus z times standard error. So that's critical value. From mu 0, I went to the right by z times SE. But X bar is less than that, so it falls in the blue region. So that's the same as accepting H0. Now, let's manipulate this a little bit. Oops. Subtract mu prime from both sides. Subtract mu prime from both sides, all right? And then divide by sigma over square root of n from both sides. So divide by sigma over square root of n. And divide by sigma over square root of n. And divide by sigma over square root of n. Consequently, everything goes out. and this is that. So from here, I just algebraically manipulated and got this. So this expression and that expression are the same. So same probability, of course. And that's why second line and third line are the same. Now, look at the third line here. What's this quantity? X minus mu prime, which is a center, because, you see, and condition is mu is equal to mu prime, so centered around mu prime. So n minus center over SC, wait a minute, this is a z-score. So this whole thing, as a matter of fact, is equal to z value, oops, z value, z-score, is less than this quantity, and now I don't need this plot anymore because I'm already using normal. So this is z-score. Z-score is less than this. Wait a minute, probability z-score is less than something. That is normal CDF, the cumulative distribution function of the normal distribution. That's precisely what this is all about. And addition is commutative, so I switch the order. This plus that, I switch the order. That's because our textbook is written like this. So what do you get? Beta value you can find out from this computation, and you can use this computation to find out the probability value. And what if you have the second case like this? Similar computation, except that the direction of the inequality is reversed. So direction is reversed. So it's the other way around. Z is greater than this. So it's 1 minus normal CDF. So using these as formulae, you can calculate the probability values. So in this problem, you can use probability value approach. Beta of mu prime is just normal CDF of this. And Z alpha, it is, and z-score associated is to that 1%, 99%, 1% to the right, so 2.33. And this part, you have to actually calculate z-score computation. Add them up, you end up with negative 0.34 something, same as before, and of course, you get same probability as before. You see? Same answer as before. Now what about the third problem? And so set up this normal CDF equal to normal CDF from this from beta, the second graph. So normal CDF from here and normal CDF from there, and set those two equal. And setting these two equal, you get equality of this z values, z-scores. So from here you can solve for n and end up with the same answer as before. This is probability value approach preferred by our textbook out there. Not me, because it's not as graphical as before. But if you prefer, and if you prefer to use formulae like this, go ahead. I'm not going to stop you.